Okay, hi folks, this is the video for section 3.4 for probability and statistics for the computing sciences. This section's on the binomial distribution. I'll apologize ahead of time if there's some barking in the background, but we've got a lot of neighbors with dogs and it's just too nice to keep the window shut. Nope, there it is. So anyway, I guess I just have my critics out there. In talking about the binomial, this is the first of the named discrete random variables type of experiment and scenario where you have a certain set of underlying conditions. As you'll see in the videos for 3.5 and 3.6, there are different random variables, discrete random variables with specific conditions, and they have different names. For the binomial, we've got the set here. I'm not going to be redundant by just reading everything here. You've got everything in front of you, but I'll mention these things as we go along to some extent. Anyway, so as far as the underlying conditions, I don't know if any of that made sense. Anyway, here we go. First off, we have a fixed number of trials. That number is represented by n. That represents how many times we repeat a procedure, or statistically or probabilistically what we call an experiment. Each time we undergo one of these trials, we break the different outcomes up into two events called a success and a failure. The success and the failure are complementary events. There is no outcome that satisfies both a success and a failure. And the big thing to recognize with these terms is that success doesn't necessarily mean something that's good, and failure doesn't necessarily mean something that's bad. Basically, successes are the outcomes that we're counting. That's the thing to remember. The history of this is that the model was commonly used in games of chance, so a success was considered a win, and that's where the term came from. But in this case, or in the general case, it's whatever it is we're counting. So anyway, on each trial, the probability of success is the same. It's denoted by a lowercase p. And outcomes from one trial to the next are independent of each other. So a random variable y here is equal to the number of successes that we have in the n trials. So smallest possible value of y is 0, meaning we'd have all failures. Largest value is n, which means we'd have all successes. And we could have any integer in between those two numbers. Okay. So, as far as the mass function's concerned, we can actually build this one using the underlying conditions. So what I've got written here is a situation where in our n trials, the successes come first, and then the failures come afterwards. So y would be the number of successes, n minus y would be the number of failures. And because of the independence, the probability associated with those y successes would be p to the y. The probability associated with the n minus y failures would be 1 minus p to the n minus y. And one thing that you'll note from here on out is that we use q to represent 1 minus p. So that'll actually be p to the y times q to the n minus y. Okay, well, like I said, that's one arrangement where we have all the successes followed by all of the failures, but that's not the only possible arrangement. So we have to count how many of those exist. The easiest way to think about this is that there are n trials. So if you were to write down n slots, each slot getting either an S or an F, the question is how many different ways could we place the S's? And that's going to be equal to n choose y. We're just picking y of those n slots to get the successes. So our mass function here is going to be equal to n choose y times p to the y times q to the n minus y, again for the set of y being 0 through n. Pardon me here while I change pages. Okay. Whoops. Okay. The pages are out of order here, I'm sorry. Okay, so for our first example, before we get into using the technology for doing the calculations, here's what we've got. We've got a soda bottling plant, and what they do in a standard quality check is that they're going to select bottles at random and measure the contents of the bottle. For their own profit purposes, they're worried about overfilling the bottles, but you can only put so much extra in before the bottles run over. But from the customer standpoint, they certainly want to make sure they don't underfill them too much. So on the past history, what we've got here is that 6% of all bottles are underfilled by more than an ounce. So what they've done here is they've chosen 35 bottles at random, and our question has to do with what's the probability that the number of bottles that are underfilled by more than 1 ounce is, and we've got three different situations here, that it's 2, that it's more than 4, and that it's between 1 and 5 inclusive. So, going back to our underlying conditions, and our number of trials is 35, corresponding to the 35 bottles that were chosen. A success in this situation would be a bottle that's would be that the bottle is underfilled by more than 1 ounce. So as you can see, success doesn't even necessarily mean something that's positive. It could be meaning something that's negative, but that's what we're counting here. The value of P in this case is 0.06, corresponding back to the 6% we had up here. Okay, and anytime you have random selection, that's what gives us independence here. So as far as the mass function with values substituted in, that's what it would look like if you were to substitute in the 35 for N, the 0.06 for P, and the 0.94 for Q, noticing Y is going from 1 to 35. Okay, so for these three different scenarios here, in the first case we're looking for the probability that Y is equal to 2, the second case that Y is greater than or equal to 5, and the third case that Y is between 1 and 5, again inclusive, so we have the or equals on both ends of that inequality. In the first case, it's a straight plug and chug, putting the value of 2 in for Y, and getting 0.06 squared, and then 0.94 to the 33rd, that 33, implying that there are 33 bottles that are not underfilled by more than 1 ounce. In the second and the third case, we've got summations corresponding to the appropriate values of Y that we're working with. So in the second case, anything from 5 on up to the maximum, which is 35, and in the second case from 1 to 5. And you've been told what those, or shown what those mathematical expressions work out to be. So 0.278, a little bit over 0.056, and a little bit short of 0.87 in the third case. Now the first one's pretty easy to just plug and chug in your calculator without needing any special functions, but the second and the third are a little bit more. So the calculator has some built-in functions for this. If you haven't gotten your calculator out yet, this would be a good time to pause the video and go do it. We're going to go through the instructions. I've got my 84 with me here. I'm sorry I didn't get the 89 after I got injured. So, but regardless of which calculator that we're going to use, we need to access the distribution function menu. All of you have got that on your calculator. In the case of the 83s and the 84s, you're going to press the second button and then hit the VARS button, which is just below the down arrow in the upper right hand corner. On the TI-89s, you're going to enter. You're going to hit the stats list editor icon, the same one that we did to get where you could enter data earlier in the semester. And then once you get in there and you're seeing the lists, there are F keys up at the top, and F5 is the key for the distribution menu. So go ahead and do whichever one it is. At this point, you will be seeing the distribution menu, and I'll get my calculator out here so you can see this. Or at least so I can, hope you can see this. Okay, so anyway here, as far as the 83 and 84 are concerned, let's see, that doesn't focus too well. So right there is the vars button, right there. This is always fun. So we're going to hit second, and then we're going to hit vars. And up here, we've got the distribution menu. It's going to look a little bit different on the 89 than it does on the 83 and 84. At this point, you can't see the binomial functions. Those are farther down in the list. But there they are right there. Binom PDF and Binom CDF. On the 89s, it actually says binomial PDF and binomial CDF. The way that these functions work, the PDF function is what you use in an equal to case. The CDF function is what you use when you're working with a range of numbers. So if you're on the 84 or the 83, the CDF gives you the output for the less than or equal to case. On the 89, you can put in a lower and an upper endpoint, and you have to get the probability directly. On the 83s and 84s, we have a little bit more work to do. That's on your notes here. But for the first case here, we had the probability that x was equal to 2, so that would be the PDF case. So I'll go up here and choose the PDF. Okay. For those of you who have the 84s, if you've got the new operating system, you'll be seeing a screen that looks like what we have here, just not with the values put in. And you have to put in the number of trials, or N, P, and the calculator uses X instead of Y, in that order. For those of you who do not have the newer operating system, or you have an 83, what you will be seeing right now, and I'll show it to you once I get this completed, is you'll be seeing the actual function binom PDF up at the top of the screen with a left parenthesis, and it's waiting for you to enter stuff. Now, what will happen is you'll enter all three numbers separated by a comma. The comma button is just above the 7. So in this case, n is 35. You can move down and type in 0.06, and then the appropriate x value here is 2. Okay. For those of you with the 89s, you have a dialog box that's asking you for the same stuff. You can just enter them in a similar order to what we did here. And when you're done on the 89s, you can just hit OK. For those of us with those of you with the 84s, with the new operating system, you're going to go down and move to paste and then hit enter. For those of you with the 83s or the older operating system, for the 84, you're going to put in the right parenthesis. And what you will end up seeing on the screen when it's all said and done is what you're seeing right here on the 83s and 84s. There's binom PDF, and then there are your values separated by commas. You hit enter, and there's the answer, which is just a shade short of 0.278. Okay, so that's how we handle that situation. Now, for the binomial CDF situation in part B, we wanted the probability that x is greater than or equal to 5. So for those of you who have an 89, you're going to go to the binomial CDF. With the 89s, which you have to put in is the value of n, the value of p, the lower end point of the interval you're interested in, and the upper end point of the interval you're interested in. So though in your dialog box, you would put those in that order, 35.06, and then we've got 5 to 35 here. Okay. Now, for those of you with the sorry about that. For those of you with the 83 and the 84, the CDF calculates the probability of being less than or equal to a certain value. We want the probability that y is greater than or equal to 5. We can't do that directly, so what we're going to do is we're going to calculate the probability of the complement. Complement of y greater than or equal to 5 is going to be y is less than or equal to 4. So we're going to call up the binomial CDF, and then same entries, same style of entry as we did in the PDF. We've got n, p, and x or y, whatever it is we're using. So 35.06 and 4. We plug that in, and then we're going to subtract that result from 1. And that will give us the desired probability that was on the previous page. Now, in the third case, we wanted the probability that y is between 1 and 5 inclusive. For those of you with an 89, this is basically the same type of thing that we just did in part B. Lower endpoint is 1, upper endpoint is 5. For those of you with the 83 or the 84, what we're going to do here is we're going to start out by finding the probability that x is less than or equal to whatever our upper limit is. So that's binomial CDF 35.065, and then we're going to subtract out everything that comes below that that we don't want. Now in this case we wanted 1 to 5. So the only thing that's less than 5 that doesn't fall in this interval is 0. So over here we've got binomial CDF 35.06 and 0. If we had wanted the interval from 2 to 5 inclusive, then we would have had a 1 here instead of a 0. For those of you who are thinking about it, if you're doing this for 0, the CDF and the PDF will give you the same value, but I'm stressing the use of the CDF here because if you're using anything other than 0 in here, the PDF and the CDF will not give you the same result. Okay, so with that, another example here, hopefully one a little near and dear to your heart. So we're working with a pseudo random number generator here and a little bit of unbalanced zoom. Sorry, I never found my tripod. So anyway, so what it's supposed to do is produce a sequence of random numbers that are supposed to, or sequence of numbers that are supposed to mimic random behavior. So if we're looking at the interval 0.25 to 0.6, 35% of all of the numbers produced by one of these generators are supposed to fall in that interval. And so let's suppose here that we choose 15 generated numbers at random, and we're going to let y equal the number of generated numbers that fall in the interval from 0.25 to 0.6. And what we're going to do here is we're going to find 3 probabilities. The probability that y is equal to 7, that y is less than or equal to 3, and that y is between 5 and 8. Again here, just to show you, I've written out the form of the mass function, substituting in n equals 15 and p equals 0.35. And as you see over here on the right hand side, y goes from a minimum of 0 up to a maximum of 15. The 3 probabilities that we want here are the probability that y is equal to 7, the probability that y is less than or equal to 3, and the probability that y is between 5 and 8 inclusive. Regardless of the calculator, the first case you're going to be using the PDF, and in the second and the third you're going to be using the CDF. Again, I've written out the summations here so that you can see those, but as far as the calculator functions are concerned, the PDF, you're going to use binomial PDF, n is 15, p is 0.35, and x, or y in this case, is 7. And we've got a probability that's a little bit short of 0.132. In the second case, for those of you with the 89, you're going to use binomial CDF 15.35, 0 to 3. For those of you with the 84s, because we're and 83s, we're looking at the less than or equal to case. So we've got 15.35 and 3. We don't have to do anything additional with that because we're looking at the less than or equal to case. And regardless of which one you've got, we're a little bit short of 0.173. In the third case, we're going from 5 to 8 inclusive. So for those of you with the 89, down there at the bottom, 15.35, 5, and 8. For those of you with the 84s and the 83s, we're going to do the probability that y is less than or equal to 8, and we're going to subtract out the probability that y is less than or equal to 4. So we've got the binomial CDF. The last number is 8, and we're subtracting out the binomial CDF where the last number is 4. And again, that will give us our answer, which is about 0.61. Okay, now Last topic. Sorry, I know it just got dark. Haven't gone anywhere. And I'm sure YouTube's going to have fun with that. Okay. So last thing, mean, variance, and standard deviation of a binomial random variable. In this class, we don't go through the derivation, but using the definition of expected value, there's what the summation would look like. And there's a bunch of algebra that's shown in your book. If you follow along with it, what you find out is that nice big expression there, thanks to a little bit of cancellation and to work with in the binomial theorem, all of that simplifies down to n times p. In the case of the variance, there's your formula right there, again using the definition of the variance of a discrete random variable, and that summation works out to be npq. Okay, reminding you back of one thing in section 3.3 is that the variance of y can be calculated as the expected value of y squared minus the square of the mean. If you're looking for the expected value of y squared, if we just go ahead and solve that expression for the expected value of y squared, it's the variance of y plus the square of the mean, and that is what you see right there in this case, npq plus the square of np. So for our two examples, we had two binomials here. One was with n equals 35 and p is 0.06, and the other is with n equals 15 and p equals 0.35. If we plug our values into those formulas, what we're seeing here is in the first case, the average number of bottles that are underfilled by more than an ounce is 2.1 in a group of 35. The variance is 1.974, and the standard deviation is a shade over 1.4. In the case of the pseudo-random numbers, the expected number of numbers that will fall in the interval 0.25 to 0.6 in a group of 15 is 5.25. The variance is 3.4125, and standard deviation, the square root of the variance, is just a shade short of 0.185. I also gave you the calculations of the expected value of y squared down there so that you could see them. We're not going to put an interpretation on those right now, but just knowing that formula will come in handy in different places, so just trying to reinforce it here. Okay, that's it. So I look forward to seeing you on Tuesday, and have a good couple of days. Bye.